In the previous skill, we talked about when you would need to use this newfound thing called transmission line theory. Now we're going to dig into it a little bit more and derive the key equations as to what that actually means. So at the end of this module, what you need to be able to do is to just have an understanding as to what the different segments, different components are to model a short strip of transmission line, and be able to describe and ideally derive the basic equation that governs the change in voltage and the change in current over a short segment of transmission line. A transmission line during this course, the way that it will mostly appear is something like this. So again, the main difference between transmission line and what you're dealing with is the fact that these wires now have to have this separate representation, which is what we're calling the transmission line. In this case, we will represent it by these two rectangles here. So usually what you will have is you have this generator, which has a source impedance, and then over here, you're going to have your load. And sometimes in other places, you might see it drawn this way, where you have the generator going to ground. Basically what they'll do is they'll just draw the upper part of it and then have the rest of it go down to ground. And or some people, you might also see it like this, where they actually draw and show you how the whole thing is bundled into a nice little coax and then comes back down, and your load is going to be over here. So this is the artistically correct way to draw it. Now, what we're talking about is that I want you to take a closer look at is to start by looking at what happens for an infinitesimally short length of the transmission line over here. So the circuit equivalent of a transmission line is going to look a little bit something like this. So let's draw it out, look at the basic components, and then use that to derive the basic equation that governs a transmission line. So what happens inside a transmission line can be stated quite easily is that on one hand, the current doesn't want to change immediately, and so that takes place in the form of a series inductance. So we're going to have this little bit of series inductance. When we talk about these inductance, one thing important to note here is that this is an inductance per unit length. So this L is actually in units of Henry per meter, not just Henrys like you would usually see. Okay, so what this basically is saying is that you have an inductor that's in series, which means that the current, if you change the current instantaneously, the current in the transmission line is going to have a little bit of a lag. And then separately, the same thing also happens to the voltage. So you end up having a shunt capacitor. And what the shunt capacitor means, remember, a capacitor starts out as a short and then eventually becomes an open circuit. So what that means is that the voltage won't really react to whatever's going on back here immediately. And so we show that through a shunt capacitor, which again is in units of capacitance per length. So again, remember that this capacitance is actually in units of Faraday per meter, not just Faraday. So you have to multiply it by the unit length in order for it to be capacitance in the traditional sense. So again, current doesn't want to change immediately, the voltage doesn't want to change immediately, and then separately in alongside with this inductance and this capacitance, they're not ideal inductors and capacitors in that you also lose some energy along there as well. So over here, we're going to have a resistance per unit length, and then over here, just to make the equation look nicer, instead of the resistance, we're going to use the term the conductance, which is in Siemens per meter. So again, same thing. It's going to be G delta Z And the main reason that we want to use the conductance instead of the resistance is we want to be able to say that when R or G respectively is 0, that represents the ideal situation. So in this case, if R is less than 0, since this is in series, that means that no energy is lost. If G is equal to 0, in this case, because G is equal to conductance is simply the inverse of the resistance. So if G is equal to 0, that means the resistance is infinity. So this is an open circuit and you don't have any current leaking over to the other side. But just remember, it's basically the inverse of resistance. And then here you have it on the other side. So on the other side at the output, you will have the voltage at location Z. But now since this is 1 delta Z length further, this is now V of Z plus delta Z. And then over here, you have the current, the outgoing current, which is I of Z plus delta Z. Oh. And actually, this is also a function of T. So again, let's just summarize the units really quick. So L is in henries per meter. R is just resistance as we know it, but per unit length, ohm per meter. G is Siemens per meter, but this is also 1 over ohm meter. Just put that there in case since we don't really talk about things in terms of conductance as much. And C is just your usual run-of-the-mill capacitor, but also per unit length. So to come up with the key equations that govern transmission lines, we simply run a Kirchhoff's voltage law calculation to understand how the voltage changes, and then we rearrange it, and then we also use Kirchhoff's current law to write it out, rearrange it to see how the current behaves. So let's just start out with Kirchhoff's voltage law. So from Kirchhoff's voltage law, we're going to look at this little loop over here. So what that tells you is that the output voltage, Z plus delta Z T, is going to be equal to the input voltage, and then minus the current drop. So the current drop is going to be so the current drop from this end over here to this end over here. So the voltage drop, the voltage drop from there to there is going to be the L di dt minus R, the resistance, times the current. So this is just straight up Ohm's law, but again, the resistance is ohms per meter. And actually, if I were to be truly accurate, since the current is a function of both time and position, this is actually going to be the partial differentiation of I and T. So I'm just going to use a fancier D to describe that. So with that, what we can do is we can rearrange. Note we have a Z plus delta Z here. And then over here, we have just a nice Z of T. So if we move this over and divide everything by delta T, we're going to end up with a nice little basic definition of a derivative. So let's just So one of the things here is you see there is V of Z plus delta Z. Over here you have VZ of T. So if you take the difference between these two and divide it by delta Z, you're going to get the definition of a derivative. So let's just start by just taking the limit of Z goes to 0, and then we're going to subtract this V of Z over. So you have V of Z plus delta Z minus V ZT is equal to minus r delta z I ct minus L di dt delta z. And then what we can do is we can divide the delta z over. So we're going to divide that over, so we can forget u, and then take the limit of delta z goes to 0, which gives us the definition of the derivative, and that gives us our first equation, where we have dv dt, and again v is a function of both z and t, is going to be equal to minus ri ct minus L di dt, and again this is a function of zt. So this is your first transmission line equation. And then we can also do the same thing with Kirchhoff's current law. So if we do Kirchhoff's current law, this time I'm going to write it further to the left so that I don't run out of room. We're going to do the same trick. So we're going to apply Kirchhoff's current law. So the next thing we're going to do, apply Kirchhoff's current law to this node over here. So Kirchhoff's current law, if you look at that node, the current coming out is the quantity we're looking for. So the current on the other end, so I of z plus delta z t. And that is going to be equal to the current coming in, which is going to start out with I of zt. And that current's going to go through this and this. And then some of it's going to go here, some of it's going to go here, and some of it's going to come out. So the part that goes here, that goes through the shunt capacitor, is going to be minus c delta z dv dt of zt. And you're also going to have some current going through this shunt resistor here. So if you write it in terms of the conductance, it's also going to be minus g delta z v of c and t. And then we're going to do the same trick. So we're going to move this I of z of t over, and then we're going to divide the whole thing by delta z. And now we can do the same trick, where we move Iz of t over to the other side and wrestle our way to get a derivative. And so let's move the Iz over. So we have z plus delta z t minus I of zt is going to be equal to, let's see if we wanted to keep the formulation the same, let's put the conductance in the first part, so minus g v, then let's just put the delta z over here, knowing what we're about to do to it afterwards, minus c dv ct dt, and then there's the delta z. And then just like what we did last time with our friend and when we're doing Kirchhoff's voltage law, we're going to move the delta z over, and then take the limit of delta z goes to 0, so that we are dealing with a very small portion of transmission line, in which case this now turns into dv d, and this now turns into partial derivative of I with respect to t. So using that, we now get our second transmission line equation, where di ct dt is going to be equal to minus g v ct minus c dv dt. of ZT. So you can now see these are the two governing transmission line equations that we'll be basing everything off of. So you see one's a partial derivative of V with respect to, there should be distance. One of the problems with these virtual lectures is none of you brilliant students are here to correct me, and it seems that I have made the same mistake over here too. I'm okay with that if that increases your retention. So you have a partial differentiation of the voltage with respect to distance is dependent on di dt. And then similarly, when you look at the current change with respect to location, di dz, is dependent on the time derivative of the voltage. And so one of the other things that will become relevant is we're going to rewrite these equations and take a look at what the solution is going to look like. And that will lead us into the next skill.